This video is on power and is for GCSE Physics and Combined Physics, and don't forget to like and subscribe. In a competition to see who can move the individual 100-gram masses onto the same height table, who will be the most powerful? As the masses are the same, 100 grams, and they are being moved the same height, then the same amount of energy is being transferred from a chemical store to a gravitational potential store. When using these kettles to boil the same volume of water with the same starting temperature, how can we tell which is the most powerful? As the volume of water is the same, the mass of the water is the same. The temperature change is also the same as the water goes from the same starting temperature to boiling, 100 degrees C. This means that the energy transferred from the heating element to the thermal store of the water is the same. So, who is the most powerful? The answer to both is the one that completes the task in the shortest amount of time. To work out the power, we take the energy transferred from one store to another and divide this by the time taken. Time needs to be in seconds. A more powerful device transfers more energy per second than a less powerful one. Power is the amount of energy transferred from one store to another every second. Anything divided by time, as energy is to calculate power, can be described as rate of. For example, acceleration is the rate of change of velocity. And this is because the equation for acceleration is change in velocity divided by time taken. So that makes the definition of power the rate of change of energy transfer. And because work done equals energy transferred, power is also the rate of doing work. Power questions come up in every Paper 1 exam, so it's really important that it is properly understood. As power is both the rate of energy transfer and the rate of doing work, it has two equations to represent it. P equals E on T, or power equals energy transferred over time, and P equals W on T, or power equals work done over time. The units for these, power P is in watts, capital W, work done, also capital W, is in joules, capital J. Energy, capital E, is in joules, capital J. And time, little t, in seconds, little s. For these equation questions, you may have to convert some units. So remember, 1 kilowatt is 1,000 watts. So for example, 3 kilowatts is 3,000 watts. And 1 minute is 60 seconds, so 20 minutes is 1,200 seconds. Power is useful as we can use it to easily compare devices that transfer energy, either mechanically or electrically. You'll do more about power in the electricity topic. This kettle is rated 1,500 watts, and this kettle is rated 2,000 watts. Because the power rating tells us that more energy is transferred per second in the silver kettle, we know that it will boil faster than the purple kettle. This lift has a motor of 15 kilowatts, and this lift has a motor of 12 kilowatts. As 1 kilowatt is 1,000 watts, then we are comparing a lift motor with a rating of 15,000 watts with one of 12,000 watts. More energy is transferred per second in the 15,000 watt motor, so if both lifts are moving the same mass, the same distance, then this will be the faster lift. Two lifts are exactly the same except for the power of their motors. Lift A has a motor of power 15 kilowatts, and lift B has a motor of power 12 kilowatts. They carry the same mass, 1,250 kilograms, and they carry that mass the same distance, 14 metres. What is the difference in time taken? First, we have to work out the work done by the lift. As work done is the same as energy transferred, we can use the equation for gravitational potential energy. So for lift A, gravitational potential energy, EP, equals mgh. Substitute in the numbers, and that gives you EP equals 1,250 times 9.8 times 14, and that gives us an answer of 171,500 joules. If we do the same with lift B, we find that we get the same answer because the inputs were the same. We had the same mass, the same gravitational field strength, and the same height. We can now use the power equation to work out the time taken for each lift. Power equals work done over time, but for the power, we need our power rating to be in watts, not in kilowatts. So to convert from kilowatts to watts, we need to times by 1000, so 15 times 1000 gives us 15,000 watts. Substitute that into the equation, gives us 15,000 equals 171,500 divided by T. Rearrange that for T, calculate your answer, and that gives us 11.4 seconds. For lift B, we do the same thing. We need to convert kilowatts into watts, so 12 times 1000 gives us 12,000 watts. Substitute this into the equation, 12,000 equals 171,500 divided by T. Rearrange, calculate, and our time is 14.3 seconds. Now the question asked us for the difference in time, so we now have to calculate that. So 14.3 minus 11.4 gives us a final answer of 2.9 seconds. Dinorwig Power Station, a hydroelectric power station in Wales, has a power output of 1,728 megawatts. The average power output of a large offshore wind turbine is 8,000 watts. How many wind turbines would, on average, produce as much power as Dinorwig? When water flows down the pipe, it causes a turbine to turn, and that causes a generator to produce electricity, which is how Dinorwig works. And when the wind turns the turbine, it causes a generator to produce electricity. This is how a wind turbine works. 1 megawatt is 1 times 10 to the 6 watts, or 1,000,000 watts. So to convert from a megawatt to watts, you need to multiply the number of megawatts by 1,000,000. So 1,728 megawatts is 1,728 million watts. Each wind turbine produces 8,000 watts, so you would need 1,728 million divided by 8,000 to give us 216,000 wind turbines to produce the same power output as Dinorwig. 1 joule per second equals 1 watt. This can be shown using the equation power equals energy over time. Power's in watts, energy is in joules, and time is in seconds. Energy is divided by time, so joules are divided by seconds. This gives us the joule per second. To get a power output of 1 watt, you need to have 1 joule divided by 1 second. And as 1 over 1 equals 1, then 1 watt must equal 1 joule per second. So a kettle rated at 2,000 watts could also be given a rating of 2,000 joules per second. And a wind turbine with a rating of 8,000 watts could also be rated 8,000 joules per second. It means the same thing. Knowing this is quite important and can be key to understanding some of the questions that can come up in an exam. This is an example of a question that you might get in a higher paper. An amount of water is heated over a period of 2 minutes. How could this graph be used to calculate the power of the heating device? No calculation is necessary. First, we need to look at what we know. We know that there's a temperature change over 2 minutes, which is 120 seconds. We know that we need to show how to calculate power, and power is energy divided by time. We know from the datasheet that temperature change only appears in one equation, and that is delta E equals mc delta theta, where delta E is change in energy, m is mass, c is specific heat capacity, and delta theta is the change in temperature. The gradient of the graph is the change in y divided by the change in x, and in this case that gives us delta theta over t. If we go back to our specific heat capacity equation and divide both sides by t, which we can do as long as we're doing the same thing to both sides of the equation, we get the following. E over t equals mc delta theta over t. And this can be rearranged slightly to give us mc multiplied by delta theta on t. Now we know that our gradient is delta theta on t. And we have our new equation of energy divided by time equals mc multiplied by delta theta on t. As these are the same, we can do a substitution. And that substitution gives us a new expression, which is change in energy over time, which is E over t equals mc multiplied by the gradient. The final step is to identify that energy divided by time, or E over t, is equivalent to power. and therefore we have power equals mass times specific heat capacity multiplied by the gradient, and that answers our question. And that's it for this video. Thank you so much for listening.